0, it's plus, 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 minus, 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 minus. So cat state in the x basis. On these 4 qubits, and we do that fault tolerantly. How do we prepare that fault tolerantly? Up there, right? We prepare it, then we check. Once you have that state, then you can to measure a weight 4 stabilizer. You can just do transversal CNOT gates, 1 to 1, 2 to 2, 3 to 3, 4 to 4. This will still copy X errors down. Except now, this compared to this circuit, this one has the advantage that a single Z error here can be copied up to just a weight 1 Z error, unlike this case where you have a single Z error is copied to weight 2. And so this is better in that sense. And yeah, but it gives you the same information. So at the end of the day, then you measure each of these qubits in the 0, 1 basis, in the Z basis, and so that gives you Z. So that gives you Z on each of these qubits. You're measuring Z on each of these qubits, and so you just multiply the measurement results or add them up mod 2, and that'll give you the Z stabilizer, which is what you want, because any X error is copied down. It'll flip the sign of the Z stabilizer. Does that make sense? So there's. One should be careful here. So let me go over this a little more slowly. The idea really is that we have a huge code, right, with maybe 1 million qubits, n qubits. But let's say one of the stabilizers is Z. So let's just on the last 4 qubits. But actually, again, it might be, let's say it's the last W qubits, which might be more than 4. And so we're trying to measure the parity of W qubits. And so what we do in general is we prepare a cat state on W qubits. Okay, now we make it fault tolerant. I don't know how to make it fault tolerant. But you know, you do whatever trick you need to make it fault tolerant to whatever distance you need. So for example, to get it fault tolerant to distance 3, you can do this kind of circuit. Or something like that. Okay, so once you have a fault tolerant to the appropriate distance D, W qubit cat state, I guess we want the dual cat state, so I'll Hadamard it. And applying Hadamard transversely is fault tolerant. It just changes weight 1 errors into weight 1 X errors into weight 1 Z errors, and vice versa. Okay, and now, so what do we know? So this cat state, it's stable. This dual cat state stabilizers are Z tensor W, and then X, I, X, so X in all pairs. Like that. Okay, and so now I do transversal CNOT gates from the set of data qubits that I want to measure the parity of into this dual cat state like that. What happens in terms of stabilizer algebra is this Z stabilizer is copied backward onto the data, but then it's canceled out by the Z stabilizer that's already on the data. And so overall, that's left alone. Then you also have X stabilizers up here copied forward onto the ancilla. But any X stabilizer on these n qubits, it has to have even weight on these W qubits, because the X stabilizer has to commute with this Z stabilizer. So it could be disjoint. It could have weight 0, weight 2, weight 4, so on. So that commutes with this, and so it's copied forward onto an even number of qubits in this cat state. But any even number of qubits, any X on an even number of qubits is a stabilizer just by multiplying these together. And so therefore it cancels out. And so therefore, if there aren't any errors, then the circuit does nothing at all. The data is left alone, and the dual cat state is left alone. if there are errors, an X error here is copied down onto here where you can see its effect in terms of what happens to this Z stabilizer. It'll flip the sign of the Z stabilizer, an odd number of X errors. And so you just measure each of these qubits in the Z basis. You take the product of the sum mod 2 of those measurement results. That gives you the sign of this stabilizer syndrome, which tells you whether an even or odd number of X errors has occurred. That's what you want. Okay. Exactly. So that's why it's useful to prepare CAD states fault tolerantly. It wasn't just an exercise that we did for fun. It's actually used all the time for error correction. Good. And then this is called Shor fault tolerance, or Shor style fault tolerance, because he's the guy who first had this idea back in mid-90s, I guess. Okay. Let me. So that's Shor style. So Shor style is you measure the syndromes one at a time. To measure each syndrome, what you do is you prepare a large CAD state in a fault tolerant way, or a dual CAD state, either way. So you use dual CAD states to measure the Z stabilizers. You use CAD states to measure the X stabilizers. There's other ways. So another scheme that people use is called Steen style fault tolerance. So Steen style fault tolerance, what you do is, well, this is just a trivial observation. If you do a C NOT gate into Ket plus, it has no effect, of course, because the NOT gate, Ket plus is a +1 eigenstate of the NOT gate. So you can do the same thing on encoded data. So this is an encoded data state. These are actually n qubits. We can prepare an ancilla that's an encoded Ket plus, again n qubits. We apply transversal C NOT gates from here to here. For CSS code, transversal C NOT gates implements a logical C NOT gate, but a logical C NOT gate has no effect because of this. So there's no point of doing this, but in fact there is a point, because when we do these transversal C NOT gates, it copies X errors down. And so what that means is you can measure this ancilla destructively in the Z basis and figure out what the errors are on the ancilla, and then you can use that to correct the data, because the errors on the data have been copied onto the ancilla. Yeah, and so the advantage of this is that, so after the X errors have been copied down, what you're going to do is you're going to measure the ancilla transversely in the Z basis, and that will get you all of the Z stabilizers. It'll get you the syndromes ±1 for all of the Z stabilizers, which means that in one step you can measure all the syndromes. So in Shor style fault tolerance, for every Z stabilizer you have to prepare a CAD state, do this, measure it one at a time. Whereas in this scheme, you get all the Z stabilizers all at once, which is nicer, especially if you have a big code that has lots of stabilizers. Or maybe if you have a high memory error rate or something, so you don't want your qubits sitting around. It's just a trade-off. Like there's no need, it's not like one scheme is better than the other. It just depends on the situation. And then there's there's some other schemes as well. But those are the main ideas that are out there.
Just in that last thing, you had a note about like the ancilla preparation. I guess that's a problem with a lot of. I mean, it's a very common thing, but like the ancilla copies the errors back to the data.
Yeah.
And you just prepare really good ancillas to prevent that.
Yeah. So that's the same issue we had with the CAD state. You can't just prepare the ancilla; you have to prepare it fault tolerantly.
Right. Yeah.
So you have to do, and it just depends on what exactly what code you're trying to do.
Yeah.
You need to apply some verification method to the ancilla to catch the errors. And yeah, like you'd like it to be